Yeah, hello everyone. It's a great honor for me to introduce Professor Yiyu to give us a great talk on the privacy preserving and efficient machine learning in healthcare. In the healthcare by the distributed edge learning. So Professor Yiyu is working is now at the University of Notre Dame and also site director of National Science Foundation and UCRC alternate and sustainable intelligent computing and director of sustainable computing lab. So basically he has a lot of papers, a lot of things to introduce. Then I think that we can just be short and then give the time for Professor Shi. Yeah, so now it's your time.
Okay, hello everyone. It's my great pleasure to be able to be here and share some of our recent research on distributed edge learning. That's what we call for, especially driven by the needs from healthcare applications. So let me get started. So the reason that we are being kind of looking at this distributed edge learning is because of the prevalence of mobile and implantable healthcare. And here I've listed some of the examples. For example, we have a skin cancer diagnosis based on the smartphone apps, where you can just take a picture with your smartphone. And the AI-based algorithm will tell you whether it's something that's potentially dangerous, that you should see a dermatologist as soon as possible, or it's something that you can just wait. And there are also like personal medical assistance, the point of care ultrasound, the cardiac monitoring, the RPPG, where you take a video of the face of someone, and then you'll be able to obtain the blood pressure, the heart rate, oxygen level, just by the facial video. So all these are examples where we can use the mobile device to really perform the healthcare. And there also on the other hand, we have the implantable devices where, for example, you have the implantable cardiac monitor. There is a deep brain stimulator where you would implant these devices into the human body in order to obtain the diagnosis, in order to deliver the treatment. So these are the potential applications where AI or machine learning algorithms can potentially benefit. But the problem with or the potential challenge for these mobile or implantable healthcare compared with the traditional healthcare or machine learning for other application is that there's a lot of regulations or constraints in terms of the privacy, in terms of the security of the learning and the inference process. For example, right, there is a HIPAA regulation that actually prevent the direct uploading of any patient data to the cloud unless you have gone through a very tedious and formal approval process, which would take a very long time to really process, if possible. And so because of that, for these potential applications, we'd prefer those kind of learning or the information or the training data essentially to be kept on the edge instead of being loaded to the cloud. And in addition, in many cases, such training data would not be fully annotated or labeled. The annotation would be limited, number one, because again, sometimes these data are from the mobile device of the patients. It's just not possible for the patients to annotate, right? And even if the data set comes from the medical centers, not directly from the patients, you would need a very specialized domain experts to provide annotation, which might be difficult because everyone's very busy, especially the healthcare professionals. And number three, the constraint would be if you want to do this kind of processing, kind of data storage, the learning on the edge, then you would have to consider that these mobile devices, these computers on the edge is not comparable. They're not comparable with the the computing power in the cloud, right? I mean, they don't have a sufficient computing, like the density for the computation. They don't have sufficient memory. So that's why it's very important to actually develop a distributed and easy to participate and privacy preserving learning framework that would actually be able to involve all the mobile devices, all the medical centers without enforcing them to share the data, right? Which would that's the main motivation. And beyond that, there is something in addition to that kind of a privacy or security constraints. There's another kind of a very special or unique challenge for the healthcare AI for healthcare is that the disparities. Because if you are learning or training your machine learning model on the edge, right? And basically the training data would be limited, even if you are able to collect the data over a period of time, it would be still considered to be small compared with the actual patient population. It will be limited in terms of their geographic distribution. It will be limited in terms of their, for example, the age, the gender distribution. They may or may not really align with what the actual distribution would be in real world. So with that, if you train a model and say, hey, it works perfect in the actual training data, but then if you want to deploy it in the real world, in the actual healthcare, in the clinical settings, then the problems will come out, right? You will see that the model might work well for the people with like shallow skin colors, but not with the dark skin colors, or the model would work well for male, but not for female, right? It will work well for some particular type of disease, but not for the other. Sometimes they even spread out to the what we call the socioeconomical status, because when you are recruiting the patients or let them using your AI algorithms on the devices, those are disadvantaged in terms of socioeconomical like status. They may not be able to afford the state-of-the-art smartphones, right? And they may not be able to really run the apps or the algorithms that require intensive computation on state-of-the-art smartphones. For example, some of our studies, we actually observed that there are still, so we know we have like the iPhone 13, right? We still see people using like the iPhones that were like 5 or 6 generations earlier than the state-of-the-art. So how do you make sure that your model, your learning framework would still be able to include those that are socioeconomically disadvantaged? These are all the kind of challenges we have, right? And if you don't take care of these, then the model you learned will be biased towards the whatever data is well represented or advantaged group in your training data set. And also because of the same reason, in actual clinical settings, we find that there are a lot of physicians, doctors who actually do not trust the machine learning or AI model, because you never know, right? I mean, they work well in the clinical, in the training setting, in a controlled setting, but you really, when you deploy them in a real world scenario, God knows like what's the performance will be if there's any degradation, if the results are reliable. So we are trying to find solutions to address these problems. And in the talk today, because we have limited time, I'm going to just focus on two of the two examples that we have studied, and they are kind of they offer some kind of unique views on two distinct problems. The first one is we call it distributed contrastive learning. They mostly focus on the data from medical centers, where we have a lot of data. However, they are not labeled, and it would not be possible for the doctors to label them. They don't have time. Basically, they tell us that we don't have time. You can access the data, but you cannot upload the data to the cloud, and we do not have time to annotate the data for you. So you have to come up with some kind of framework that you can use our data without requesting them to be uploaded, without requiring us to annotate the data. So that's the first kind of technique that we try to develop. The second one is more like for the implantable healthcare that I explained. Each individual patient would have their own device. They would collect their own data. how do we have kind of machine learning framework like federated learning that can collect or utilize the data from those kind of each individuals, and be able to provide good health monitoring and treatment. So let me start with the first one, right? So when we look at this problem back about 4 or 5 years ago, there are actually lots of federated learning frameworks already where we know the benefits would be, you don't require the sharing of the data. You can just upload the features, the model weights for aggregation in the cloud, which is nice. But at the time of our research, there was very limited work that there were a few, but very limited work in terms of unsupervised federated learning. There are some, but they don't just work very well. Especially in our scenario, we do have large chunk of medical data from each of the medical centers, but they are not labeled. They're structured medical image data. We cannot share them because of the privacy and concerns. So now, if we forget about the federated learning, if we look at just self-supervised learning on the edge, then there are quite a few different solutions. The first, one example would be the self-supervised contrastive learning, which I think everyone's quite familiar with. And if you are not, then a high-level idea would be, we have an input image, right? You don't have the label. Let's say it's for classification. You don't have the label. You don't know if it's a dog. Then you would actually form a pair of input for the image. Like if they are similar, then we call them a positive pair. If they're different, then if you do some kind of a change so that the image become different, then you're going to have a negative pair. You send them into the training framework, hoping that you would be able to push the representations from positive pairs to be as close as possible, and those from negative pairs to be as far away as possible. So that's kind of the main idea anyway. And if you look at the performance of those self-supervised contrastive learning or self-supervised machine learning framework compared with supervised learning, which is the one like the 3 red stars and that kind of that's the results from the supervised learning. And you can see that they're getting close, right? There's a gap in terms of their top 1 accuracy from the figure, but the gap is not horrible. It's not a huge gap. And so let's say, what if we just apply the federated the contrastive learning in a federated setting, right? The challenge here is that each client in our federated learning problem, in terms of the medical image processing or computing problem, is that each client would only have a small amount of unlabeled data. And the data from each medical center will lack diversity. And this problem is pretty obvious because what we have obtained or we have observed in our study in the past is that if you train a model, in most of the cases, if you train a medical model, AI model for the data from one healthcare facility, and then you apply it to the data from another one, then in most of the cases, it won't work very well. Even if the data would, they look similar visually, but you're going to see a big performance degradation when you apply the model to data from a different medical center. So there was some kind of diversity across the data from different clients, from different medical centers. But within the same center, even if you do contrastive learning, the diversity is limited. So you would have limited number of positives, limited number of negatives. You would have, all these are constrained, they are, you don't have this kind of diversity. And if each client would only focus on the contrastive learning on its own data without considering other data, then basically the client will have each client will have its own feature space, and these feature spaces will be consistent across the clients. And when you aggregate those kind of local models, those kind of inconsistent feature space will degrade the aggregate model because they are, basically you're training from kind of distinct and different, completely different, representations. That's going to be problematic. And so a kind of a more like a straightforward way to extend this idea to consider the potential features from different clients is that we allow the clients, of course you cannot share the data, but if you share those kind of features from the from different clients, which we call the remote features in this particular plot. Then the one idea in this particular example, we are doing, let's say we do the 3D medical image segmentation where you're going to have a 3D CT or MR image from different clients and in different medical centers. And those 3D medical images would be formed by 2D slices, right? And we can actually do a kind of a contrastive learning by identifying the pairs from the different local 2D slices. And we would also be able to identify or find form the positive and negative pairs for the representations from the slices across different clients. Again, by looking at the features coming from the remote clients, so that you would have those kind of feature exchange. You would be able to aggregate the model from different clients. So that's the kind of like the high level idea. Once you're done with this kind of pre-training, and then you can have the fine tuning on each of the client based on their limited annotated data. So that's a very straightforward idea. But if you want to think about the actual way of implement this, right? Like how do we form, if you want to do contrastive learning for each of the client, how do we form the positive and negative pairs? So now, if we look at the slices from, the images from the client itself, then the kind of the positive and negative pairs will be easy to define because you can look at the data from different patients in the same medical center or from the same client, right? Remember here, each client is a medical center and there are lots of patients in that client. And you look at the 3D images from each of the each of the patient in that center. We think that the same partition or the same slice from different patients, the 3D images, they would form the positive pair because they are more or less similar because they are from usually from the same 3D scan, the CT or MR scan, the same position of slice from different patients would form the positive pairs. And those from different partition would apparently form negative pairs, right? The local negative pairs. And we can actually do the same thing for those from remote, because you would think that the different partition from different patients from different medical centers would also form negative pair, right? And then they from the same patients, they'll form the remote positive pair. So basically, either you look at the representation from the patient in the same client, or that would form the local pairs, positive, negative, or you would like those from different patients from different clients that would form remote positive and negative. And then you can do the contrastive learning. You can push those negative pair representations to be further apart, pull those data from the positive pairs to be close. So that's the also pretty straightforward way. Just you would get just keep in mind that you have to include those positive and negative pairs, not just from the local features, but also from the shared remote features. And then you would be able to do the federated learning scheme. So that's what I have just explained, the local positive and local negative. Basically, you look at, we use the position or the partition across different patients to indicate whether they are similar or they're not similar. And then eventually, once you have that, then the final loss function would come from the contrastive loss of those local positive and negative pairs, and also the loss function from those remote positive and negative pairs. So in this way, each client will be able to learn from both itself and also from the remote. So the problem with this approach is that if you think about the general framework, right, for contrastive learning, you need to have the positive pairs, you need to have the negative pairs, and then that will involve a lot of like feature exchange, that would involve a lot of communication, and we know that it's critical to reduce the communication cost in the federated learning. So what we're trying to do is that maybe we can only use the positive pairs without requiring the negative pairs. So, and then that is already being addressed in the BIO setting, the BIOL structure learning, where you would use actually, if you just a high level review of this BIO structure is that when you have an input image, instead of requiring to form the positive and negative pairs, here we just have two encoders. One is called the online encoder, one is called the target encoder. And the online encoder has both the projection head and the prediction head, and the target encoder only has the projection but not the prediction header. And during the training process, you would continuously update the online encoder. You'd keep training it. And then, over the time, this target encoder is being kind of updated using the moving average of the coming from the online encoder. And the idea is that you would be able to form a loss from the online encoder and a delayed view of it, the kind of bootstrapped view of it, so that you will be able to form the loss function without the need to form the negative pairs. So it's more like a self kind of supervision, looking at from the online and the target encoders. So this, if we form a self-supervised federated learning using the BIOS kind of scheme, then at least you don't have to exchange the negative features. Only the positive features need, from the negative sample. You don't need the positive samples, right? That would help. And now, then we ask, can we do even better than that? So remember, in the BIO setting, you have the online encoder and you have the target encoder, right? And if you do a straightforward implementation of that, then each client will need to upload both the online encoder and the target encoder. At the server side, you have to aggregate both the online encoder and the target encoder, and then each client will need to download the online encoder and the target encoder. So there's two copies of the encoders, right? So, and then we are thinking, since the target encoder actually comes from the, online encoder anyway, maybe we would let each client only download the online encoder from the global, instead of downloading also the target encoder. So let's say that now so Kasai, let's say we use Kasai to annotate the target encoder. We use theta to annotate the online encoder, right? And big F means the global and the small f means local. So that's the annotation. Now, let's say in iteration R+1, each client has downloaded a copy of the global online encoder. And of course, it also needs the global, the target encoder, but doesn't have because it's not downloaded. So the question is, maybe we can, at local computation, we would approximate that global target encoder. So the way we target it is at the server end, we compute the distance measured by L1 norm between the weights of the global target encoder and the global online encoder. So that's called the D. So we have a distance to see how far are the weights between these two encoders. Remember, one is actually the moving average of the other. So they're not too far apart, right? So we compute the distance, and the server will tell each client that distance, how far are the global target encoder from the global online encoder. So that it's a scalar, D. So there's also almost a zero communication cost. So that's being distributed to all the clients. Now the client has the global online encoder. It has this distance. Then the client will iteratively perform a local update by updating so the Kasai, remember, that's the target. It's the local target encoder. We iteratively update the local target encoder using the what you have obtained from the global weights theta, the global online weights theta. So you would keep updating it, and then eventually you would look at, hey, from my current local target encoder, is it also within the same distance d or even smaller than the same distance to the global target encoder, sorry, to the global online encoder that I have downloaded? So again, the high level idea is, I know in the server, the online encoder, the global online encoder would be close to the global target encoder. They are similar, right? Not too far away by design in the BO. So let's say we only download the global online encoder that keeps getting updated. We do not download that moving average kind of updated. And then we update, instead of directly downloading the global target encoder, we directly continue to train or update the local target encoder, hoping that this local target encoder will eventually become a good approximation of that global target encoder instead of having to download it. That will save you about half of the downloading cost, right? That's the idea. Now by this way, we call it PTNU version, we have eliminated half of the downloading cost. Then the next step would be, can we do even better? Can we further reduce the communication cost? That's what we call the DP. And the idea is that for the, what can we do for the upload communication cost? In the straightforward case, each local client will have to upload both the local target encoder and the local online encoder. You have to upload two. The question is, can we only upload one? Right? Now, the idea here is that we can actually only upload the local online network, and we don't need to update the local target network. So if we only upload the local online network, FKSI, then essentially you will tell from each client, you would actually be able to tell, hey, from my computation, what is my local in this local device, what is the distance from my local online encoder to the global, from my local target network, the target encoder, and the downloaded global online encoder. I can compute their distance. So at each local client, I know what's that distance, how far I am. And then if I tell the global server, hey, this is my distance to the target, to the global target. Hey, this is my distance to the global target. And then eventually, if the server knows from each client what's that distance to the global target, and then we aggregate those distance, then we think that will give you a good representation of like how far away it's the global. Eventually, it will be the global if we would have this global local target network uploaded, aggregated, what would be that distance to the online network, the global online network? So that's what we call the DP. The DP is the average of all the local distance. And we upload them to the server. We scale it by a scaling factor alpha that can be calibrated. We think that's a good indicator on the global, what's the distance from the global target encoder to the global online encoder. Okay, so this is a way to estimate that distance without having to have each client directly upload the target, its own local target encoder. They only upload a distance. At the global, we estimate that distance. And why do we only need to estimate the distance? Why do we not need to compute actually the aggregated global target net encoder? That's because in the previous step, if you look at here, what do we need to provide from the server? Well, only a distance. because in this step, we have eliminated the need to download the aggregated global target network anyway, encoder anyway. So why do we need to compute it, in the aggregation step? We just need that distance, right, to inform each client. And how do we get the distance? We get them from each client. We take the average. So this way, in this entire framework, at this point, we have completely eliminated the aggregation, the download process of the global target network. There's no more global target network. There's only an indicator of its distance to the global online network that gets updated anyway in the learning process. So that's the high level idea. And we tried some experiments. We tried our the ACDC MRI 3D MRI data set, which contains 100 patients. We randomly split them into 10 folds, 10 partitions, and each partition is assigned to one client representing one, maybe medical center, right? So each client have 10 patients. And we find, once we're done with this unsupervised contrastive learning, we do the fine tuning with limited annotation. We annotate 1, 2, 4, or 8 patients from each client. We look at the results. And for the fine tuning, we try the local fine tuning where each client will only fine tune its model based on its own annotated patients, or we do federated fine tuning where, again, we fine tune the model in the federated learning setting, in this way supervised, using the annotated clients from each client. We also tried the generalization on the transfer learning, like, hey, we used unsupervised federated learning, and then we transfer learning it to another data set that's our data is sparsely annotated. So here are the results. This is for the local fine-tuning on the data set, where N, the big N, indicates how many annotated patients we have, from 1 to 8. And apparently you can see that, the more patients you annotated and the higher the results will be in terms of the accuracy for the segmentation. And in addition, if you look at the last few, the FCL, that's the straightforward implementation of contrastive learning where we have both the positive and negative pairs. The FCL OPT is the one that is built on the BYOL, the BO, where we have eliminated negative samples, negative pairs. The FCL PTNU is where we have eliminated the download of the global target network encoder. And the last one, PTNU DP, is our version that we have eliminated both the upload and download of the target encoder. And apparently you can see that as we remove more, in fact, okay, so the BO-based federated learning, contrastive learning without without negative pairs, that's FCL OPT, actually able to achieve pretty good results, comparable or sometimes even higher than the one that we built with both positive and negative pairs. And by eliminating the global target encoder, we see a little bit of performance drop, not by a lot. And by further eliminating the upload of the local target encoder, we see some further kind of degradation. But again, they are not horrible. It's a slight degradation. The last 2 rows, you can see that. Similar conclusions can be obtained by federated fine-tuning. The results here are better than the local fine-tuning, which would be expected. And we have similar conclusion. And especially in this case, if you use the BO-based unsupervised contrastive learning, you can see that the performance is always better, consistently better over the one that have both the positive and negative pairs. And also we tried the transfer learning by fine-tuning the model, not on the original data set annotated, but on a different data set. It's HVSMR. And then we see that by pre-training the model using our method on ACDC and then transfer it to the HVSMR, you can see that the results is conclusion similar. We have the state-of-the-art performance on the 2 versions, the straightforward versions without reducing the communication cost. And by further reducing the upload and download cost, we see some degradation, but not by a lot. This is the visualization effect where you can see, the last few are from ours and compared with the ground truth, which is the second figure on the first row. our version without the reduction of the communication cost, which is the first and the second one in the last row, they are pretty consistent with the ground truth compared with other state-of-the-art approaches. By reducing the communication cost, we start to see some kind of information loss or the accuracy loss, especially for that green and purple kind of area, but overall, still acceptable. And this is the comparison of the communication cost compared with our approach with the federated MoCo, the FedMoCo, and federated BO, the two straightforward version of previous state of the art. The first column indicates the communication cost normalized to our straightforward implementation of the unsupervised contrastive learning with both positive and negative pairs with the feature sharing between the clients. So you can see that of course, everything else would have a lower communication cost. Our method, the one that's called FCL, PTNU, DP, without eliminating upload and download of the online, the target encoder, achieves a comparable overhead compared with a communication reduction compared with the FedBO, right? And but we have higher performance compared with the FedBO in all of our versions. So we have a comparable communication cost and of higher performance. And this is a summary again in terms of what's being communicated in the federated contrast learning setting. So in our approach, the best version, the lowest, the one in the last row, we only need to have the online network and the online predictor uploaded, downloaded, basically that online encoder. And we don't need to have the target network uploaded or downloaded. So basically that the overhead is almost zero. We only need to, again, communicate that distance, which is a scalar, so it's negligible. In the PTNU setting, we only need to upload the target network, and in the FCL OPT, in the plain version, you would have to upload and download the target network. So that's the communication overhead summary. And in terms of the contribution of this work, it's a federated contrast learning. We learn good representation on distributed unlabeled data. We would have the feature exchange. So some of the biggest difference between our approach and the previous art is that we would allow the feature exchange between the clients in terms of the positive and negative pairs. And then that will allow a global contrast rather than only doing the contrast in the local setting. And we also have this structural similarity of the images across the global clients to form the pairs. So you don't need to use the labels, right? And we have communication cost reduction by eliminating the target network, upload and download. So that's the first work. And the second work I'm going to share is we call also the personalized meta-federated learning, but it's not for medical centers, but for individuals. And the application I'm going to share is the ICD. I don't know if any of you are here online or you're familiar with ICD. That is basically, it's called implantable cardioverter defibrillator. What is being used is to treat the patients with what we call the life-threatening ventricular arrhythmia. So that is the life-threatening VA ventricular arrhythmia. There are two different types: ventricular tachycardia (VT) and the ventricular fibrillation (VF). Both VT and VF are the most frequent recorded shockable rhythm that would cause the sudden cardiac death. So that means when that happens, you can have a window of like 1 to 2 minutes to deliver external shock. You probably have seen that AED box, the red box hanging in the public stations, public places. That's when it happens. You would have to shock the patient immediately. If not, then the patient dies, right? So you have a window to do that. A famous example for that, I know probably everyone here in Japan would be a football fan, right? If you have heard the story about Christian Eriksen, who is a famous player in the England Premier League, he actually suffered from the ventricular arrhythmia during a football match. But his teammates were able to actually deliver the shock on the spot. He recovered, fortunately, and received in the implantable cardioverter defibrillator. So it's something being implanted in the heart. It keeps monitoring the heart rhythm. And if this VA is being detected, then it will deliver a shock up to 40 joule of energy to bring the heart rhythm back to normal, so that you don't have to carry an AED around. Everything is being done automatically. That's the main idea. Now, how do we detect VA, right? At the center of this ICD is that we need to detect a VA. How do we detect a VA, right? Everyone here would more or less be an expert in machine learning. So you build a network, right? It may be a 1D CNN. It's a 1D cardiac signal. So why is it difficult? You have the labels, you know, hey, these are the VAs, right? You have the labels, you have the input, it's a time series signal. Well, you train a neural network, you're done, right? So that's the easy approach. This is very, very easy. And there was a paper from Stanford, from Fei-Fei Li's group, I think a few years ago, showing that neural network can achieve very high accuracy in this kind of task, because it's very easy. This is much easier than, like most of the image classification tasks, natural image class. This is a simple problem. However, if you go out and look at what are being done in industry, there are a few big companies like Abort, Boston Scientific, Medtronic. These are the big players. They have their ICDs for many, many years. So this is what's being used in their products, in the state-of-the-art industry product in the medical industry. So you can see, what is this? This is a state machine-based detection. Okay, it's based on a set of very complicated rules. You do a counting, you do a signal detection, and that was from like what? A very basic signal processing textbook. If you ask anyone, if can I write a paper using this kind of a algorithm for anomaly detection? Well, the paper will be desk rejected, right? I mean, what's the novelty here? No one's using that anymore, right? People are doing machine learning. So why don't they use machine learning? It's a very simple neural network. So the idea is, because this is healthcare, and for healthcare, if you want to use AI or machine learning algorithm, there's an FDA approval. And in order to get FDA approval, you have to convince them that your model, your product would work for most of the people. And here is the first problem that we're facing. It's called inter-patient variability. I have listed some of the, these are from our clinical studies. We work with a company that builds ICD. So these are the patient IDs. They're real patients. We developed a model, 1DCN, achieved comparable accuracy with state-of-the-art from that paper I mentioned from Stanford. Very high accuracy, close to 100%. Great. Now we apply them on different patients, right? These are on the left-hand side, they are the ECG. We call it IEGM because these signals are collected from inside, not from outside. So it's basically they're ECG signals. So apparently, look at them, they look quite different. And if you look at the accuracy on the different patients, well, you get some lucky guys, 205, patient 205 and patient 334, they get almost close to 100% accuracy. Then if you give this to FDA, well, you do clinical trial, and FDA will look at this and say, hey, what happens to patient 335? Will this patient die? Yes, he will, because the accuracy is less than 20%. Basically means that you won't be able to pick up these kind of anomalies for him. Well, for this unlucky guy, right? There are not too much better for 188 and 266 as well. Now, even for the same patient, we have intra-patient variability, meaning that if you look at the same patient, 326, patient 07, patient 20, if you look at what they're doing, depending on if they're doing the physical exercise, if they're doing like when they sleep, when they're eating, when they're excited, and they also be different. So how do you guarantee that your machine learning model would work at different time when this guy is doing different things, right? That there's no So it's naturally non-IID. There are a lot of variations. So because of that, we actually developed another federated learning kind of framework. I would not have time to go into too much detail, but the idea is that, hey, let's try to learn from the data from each different patient, from the device of each different patient, in hope that when we are aggregating the model in the cloud, we would not only aggregate the weights of the model that are trainable, we would also aggregate, we look at those non-trainable, for example, the mean and variance of the batch normalization. These are not trainable weights, right? They come, they are, we use a momentum-based aggregation. We look at the distribution of those non-trainable weights, and we, based on their similarity of these non-trainable weights, we kind of think how similar are those data from different patients. And the goal is that we should put more emphasis in the global aggregation stage to take care of those majority groups, because they represent overall performance. So the model aggregation will heavily bias towards those global, towards those most represented clients that are similar. So we sort them based on how well they're represented in the aggregation. We don't do a plain aggregation. But then you'll be asking, then how about those outliers, right? They will be ignored. And then when each of the client download the global copy of the aggregated model, when they are being trained, each client will be instructed if they are kind of their activation, or their those kind of non-trainable sets of parameters, they are far away from the global kind of the center or the majority group, they will be instructed to use adaptive learning rate to, in the extreme case, to ignore that global model. They can just continue to fit on their own data, basically, hoping that their model eventually will fit their own particular need. You don't really have to take care of others, because the model will eventually be used by this guy only. So you can kind of learn more towards its own data set, fit more on its own data set, by replacing those global non-trainable parameter with the local ones, and also using adaptive learning rate. So we conducted some experiments here. Initially, apparently you can see that we have a lot of devices. We actually, this was being done a couple of years ago, where we have some of the devices as the clients. We have Raspberry Pi 3B. We built about 20 of them. And then we use a MacBook Pro as the server to aggregate the data. But now we have a lot more than that. We have hundreds of these. It's a huge desk. We have all those devices to do the experiments. We have those signal generator to generate close to reality ECG signals representing different patients. And we run the experiments. So here are the results. We compare with all the state-of-the-art for federated learning without considering the need for the personalization on each individual client. And the rest, the four on the bottom are our design. I don't have time to cover. These are more like different versions of our method with different kind of ablations. But the last row represent our full-blown framework. And you can see that in terms of F1 accuracy, they are pretty much higher than those from the federated learning. We can get we get 3 different data sets, and they are all working fine. And this is basically the box plot showing the deviation on different test objects. Again, that's what we're interested in, how well the model will perform across different patients, right? And these are different, each box on the plot represent a different method. The longer these boxes are, the more variation you see. So apparently you can see that PM-FED, which is our proposed approach, we achieve the smallest deviation across the patients among these different methods across the 3 different medical data sets. These are also another view of that. We achieve a comparable or even higher practical performance in terms of both the training overhead, in terms of the transmission traffic, which is the one in the bottom, the network traffic, in terms of the energy consumption, because we're looking at edge devices. So energy consumption also matters. In all the three different comparisons, the training latency, the traffic, the energy consumption, our method, the PM-FET, the one in red, apparently is the best compared with all other approach. So to end my talk, I'd like to show you a demo. I know my talk is long, it's about an hour. I'd like to end it with something that's thrilling, if not exciting. All right, what I always tell my students, what's the goal about research, right? Not just to publish papers. You want to be able to make your research useful, especially it's for healthcare. So since we're talking about ICD, let's do ICD. This is we tried our implementation on an actual ICD with our industry on a clinical trial. And this is the video. On the left, I can, what happens is in order to show its effectiveness, again, approved by the regulations, the federal regulations, you would actually first induce the ventricular arrhythmia. And the way to induce that, you can see that from the ECG signal on the screen, that red, when you see it becomes irregular, that's how basically you pass a 50 hertz of small current, very small current, but 50 hertz AC current through the heart. That will induce that will induce the ventricular arrhythmia. And then the doctors will monitor and see if your device can pick up that VA and deliver the shock.
Like human or on the kid?
Which one?
You're on the bed. If it's a human or
human.
But then how can you give him induce this one? I think
that's a requirement for any implantation, for any implant, even for the product. You first have to.
It's just like a test now.
It's that because you make sure it's working. So and that's what I say. If it doesn't work, then the doctor they will have the external AED to bring it back. But fortunately, up to this point, we have done 70 studies and they are all successful. We were able to, I think, not in a clinical setting, but in real world, when the patient's out of the clinics with this device, we were able to save about close to 10 lives. We were able to detect them and get shock delivered. I also want to mention that this is also a very interesting application where usually in the healthcare you would say we have the false positive and the false negative, right? Sometimes people would say that false positive is probably okay because you just scare people, but right? Like cancer, you tell, well, you have cancer, but then you don't. That's okay. False negative is something that's more horrible. But in this case, what false positive means, false negative, of course, that's not good because you cannot pick up the event, right? The patient might die. But what the false positive means is that the heart rhythm is okay, but you think it's VA, you deliver the shock. And when the patient does not have VA, the patient is conscious. When the patient is conscious, you deliver that 750 volt, 40 joule shock to the heart. That's extremely painful. You have the pain scale from 0 to 10. That's on the scale of 10. It's extremely painful. So it's not acceptable either. So this one, you can't have false positive, you can't have false negative. They're both not acceptable. But anyway, that's a very interesting application, and we're still looking at this more to see what can be further improve it. But just to wrap up, so we have talked about two different work. One is distributed contrast learning unsupervised for medical image segmentation, mostly targeting medical centers. The other one is personalized kind of meta-federated learning. They're more for implantable devices to handle non-uniform data distribution, to handle heterogeneous hardware and models. And again, if you are interested, we have listed some of the references we have published along these works so that you can check out more details. So that's all for my talk. Thank you.